Last time in PT10, we loaded a real text dataset and turned every character into an embedding, a little learned vector that captures what each token is. But there's a hole in that picture. An embedding for the letter O is the same vector no matter where the O lands in the sentence. The model knows the what, it has no idea about the order. And order is everything. So today we fix that, and while we're at it, we build the exact batches our GPT is going to learn from. Here's the gap. The embedding table knows that O is O and R is R. It does not know that this O came third and that O came 10th. Every position looks identical to it. To a transformer, by default, a sentence is just a bag of tokens with no sense of sequence. That can't be right. So we need to inject position somehow. Why does order matter so much? Take 3 words, dog bites man. Boring, it happens. Now swap 2 of them, man bites dog. Same 3 words, same embeddings. Completely different story, one's a headline. Order flips the meaning. If the model can't tell position apart, it can never tell those 2 sentences apart. The fix is beautifully simple. We make a second learnable table. The first one is indexed by token, what the symbol is. The second is indexed by slot, position 0, position 1, position 2, all the way up to the context length. Then for each token we just add the 2 vectors together. Now the vector says both I'm an O and I'm in slot 3. Same trick we already know, a lookup table pointed at position instead of identity. And now the question that runs this whole course, what are we even training the model to do? One thing, always, predict the next token. Given everything so far, guess what comes next? The magic is that the text supervises itself. We never label anything by hand. The next character in the file is the right answer. Free, infinite training signal, hiding in plain sight inside the corpus. So how do we make the training pairs? The shift by 1 trick. Take a chunk of tokens as the input. X, the target Y, is that exact same chunk slid 1 step to the right. So when the model has seen T, the answer is O. When it's seen 2, the answer is. Every single position in the chunk becomes its own little prediction problem. One slice of text gives us block training examples at once. How big is that chunk? That's the block size, the context length. It's how many tokens the model is allowed to look at when it makes a prediction. Think of it as a spotlight. A small block sees a few characters of history, a big block sees whole paragraphs, bigger context, more to learn from, but also more compute. For now we keep it tiny, 8 tokens, so the shapes stay easy to read. Last piece, we don't want to read the file front to back in order. That biases the model toward the beginning. Instead, we grab random offsets, pick a handful of random starting points in the corpus, pull a block from each and stack them. That stack is a batch. The final shape is batch size by block. Here, 4 by 8, 4 independent windows into the text, all learned from at once. B0, overview. Okay, to the code. Batches.py is short, but it's the heart of the data pipeline. We set up the 2 embedding tables, write one getBatch function that does the random offset slicing, run it once, and decode a real example so you can see the context to target pairs with your own eyes. 2 pages, let's walk it. Up top, the usual imports and a fixed seed, so your run matches mine exactly. Then the data. We've got our encoded corpus from PT10. The whole text as one long tensor of token IDs, plus the encode and decode helpers and the vocab size. I'm printing the total token count just to ground us in how much text we're working with. Now the 4 hyperparameters that define a batch. Batch size is 4 windows per step. Block size is 8 tokens of context. EMBD is 32, the width of every embedding vector, and vocab size comes from the dataset. These 4 numbers shape every tensor you're about to see. Here are the two tables, token embedding table maps each token ID to a 32-dimensional vector, that's the what. Position embedding table maps each slot, 0 through block size -1, to its own 32-dimensional vector, that's the where. Two nn.Embedding layers, both learnable, both filled in by training later. This is getBatch, the function everything's been building toward. First line picks the random offsets, torch.randint gives us batch, size random starting points, each safely inside the corpus so a full block always fits. X is just a little vector of 4 random integers, our 4 starting positions. Then the slicing, the shift by 1 trick in 2 lines. X stacks a block starting at each offset I. Y stacks the same block starting at I plus 1. So Y is X shifted right by 1 token. We torch, stack the list of blocks into a clean, batch size, block size, tensor. Return both. That's the entire batching mechanism. 2 slices and a stack. Now we use it. Grab one batch, print the shapes of X and Y. Both should read 4 by 8. Then the embeddings. Look up the tokens to get token vectors. Look up arrange a block size to get position vectors and add them. Broadcasting handles the rest. Token embeddings are 4, 8, 32. Position embeddings are 8 by 32. And they sum into a combined 4, 8, 32. Every token now carries both its identity and its place. B7, closer plus teaser. Finally, we decode one window to make it real. Print a growing context and the single target character it should predict at each step. With the context to be O, the next character should be R. And there it is, and one step on to be OR points to a space. The data's ready, random batches, positions baked in, every token a training signal. Next time, PT12, we build the idea that made GPT possible, letting the tokens actually look at each other. Query key value, self-attention from scratch, that's where it gets exciting.